So, here's something that might have happened to you when you were a kid. You're rummaging around in a drawer, maybe your dad's toolbox or a kitchen junk drawer, and you find this heavy little object, dark and smooth, and you bring it near a paperclip or a nail, and the thing just jumps. It leaps across the gap and sticks. No batteries, no wires, no explanation anyone gave you that actually made sense. You could feel it pulling through the air, this invisible tug, and if you tried to pull the paperclip away, you could feel it resist, like the space between the magnet and the metal had become thick, had become something, and nobody around you, not your parents, not your teacher, maybe not even your science textbook, could really tell you what that force was. They'd say, it's magnetism, which is just giving the mystery a name without solving it. That's like saying, why is that person laughing? And someone answering, because they find it funny. Okay, sure, but what is actually happening? That question, what is actually happening, turns out to be one of the deepest, strangest, most fascinating threads in the entire history of science and engineering. And tonight, we're going to pull on that thread, slowly, gently, and see where it takes us. There's no rush. If you drift off somewhere along the way, that's perfectly fine. The ideas will still be here. But I think you'll find that the real story of magnetism, the human story, the discovery story, the wait, that can't be right story, is so genuinely weird and wonderful that it might keep you company for a while. Let's start where people always should start, which is at the very beginning, with a rock. About 2,500 years ago, maybe longer, people living along the coast of what's now western Turkey, a region called Ionia, noticed something peculiar about certain stones found near a city called Magnesia. The stones could attract small pieces of iron. Just like that. No tricks, no mechanism anyone could see. You'd hold one of these dark, rough stones near a bit of iron, and the iron would move toward it. The Greeks called these stones lithos magnetis, the Magnesian stone, and that's where the word magnet comes from. It's just a place name. It's like if we discovered a new force of nature in Cleveland and called it Clevelandism for the next 3,000 years. Now, the mineral itself is what we'd call magnetite today, which is an iron oxide, basically iron and oxygen locked together in a particular crystal structure. Chemical formula Fe3O4, if that means anything to you. And magnetite is actually pretty common. You can find it in rocks all over the world. But the pieces that are naturally magnetized strongly enough to pick up iron, those are rarer, and we call them lodestones. Lodestone literally means leading stone, or waystone in Old English, because eventually people figured out that if you let one of these stones rotate freely, it would swing around and point roughly north-south. But that realization came much later. For a long time, the Greeks just thought these stones were strange and maybe a little magical. And here's the thing. They weren't wrong to be amazed. Think about what they were seeing. In the ancient world, you understood forces pretty intuitively. You push something, it moves. You pull a rope, the bucket comes up. Force requires contact. That was the basic deal. But here was a stone that could reach across empty space and grab a piece of iron without touching it, that violated everything they thought they knew about how the physical world worked. It was, in a very real sense, the first encounter with a field, an invisible influence that extends through space, even though nobody would use that word for over 2,000 years. Thales of Miletus, one of the earliest Greek philosophers, born around 624 BCE, apparently thought lodestones must have souls. That was his explanation. If the stone can cause motion without contact, it must be alive in some way, because only living things initiate movement on their own. And honestly, that's not a stupid conclusion given what he had to work with. He was trying to fit an observation into his framework, and his framework said that spontaneous action requires a soul. So the stone has a soul. It's wrong, but it's a reasonable wrong. Plato mentioned magnetism too, and so did Lucretius, the Roman poet and philosopher, who around 50 BCE actually tried to give a mechanical explanation. Lucretius proposed that the lodestone emitted tiny particles, a stream of atoms, that pushed the air away from the space between the stone and the iron, creating a kind of vacuum, and the iron rushed in to fill that vacuum. It's completely wrong in its details, but notice what he was doing. He was trying to explain action at a distance using only contact forces and particles. He was trying to get rid of the magic and that impulse to replace "it just does that" with "here's the mechanism." That's the beginning of engineering thinking. That's the instinct that eventually builds electric motors and MRI machines and maglev trains. For a long time, though, magnetism mostly stayed in the realm of curiosity and superstition. People thought lodestones could cure headaches, or that garlic could demagnetize them, or that a lodestone placed under a sleeping person's pillow could test their faithfulness. There's a wonderful medieval legend that the tomb of Muhammad was suspended in midair by lodestones, which isn't true at all, but it tells you how powerful and mysterious people found the idea of magnetic levitation, even as a fantasy. But let's talk about when magnetism stopped being a curiosity and started being useful, because that changes everything. And the story takes us to China. Sometime around the 1st or 2nd century CE, the exact dates are genuinely debated among historians, and I'll be honest about that. Chinese scholars discovered that a piece of lodestone, if carved into the shape of a spoon and placed on a smooth bronze plate, would rotate until the handle pointed south. They called it a south-pointing spoon, or sinan. Now, whether this was actually used for navigation at that point, or primarily for feng shui and divination, is a matter of some scholarly argument. But the key insight was there. This stone knows where south is. It has a directional preference that's consistent, reliable, and connected to something much larger than itself. By around the 11th century, Chinese navigators were definitely using magnetized iron needles, not lodestones, but iron needles that had been stroked with a lodestone to transfer the magnetism, floating on water or suspended by silk thread as actual compasses for sea navigation. And this is huge. Think about what the compass does. Before the compass, if you were sailing out of sight of land on a cloudy night, you were guessing. You had no stars, no landmarks, nothing. The compass gave sailors an invisible thread connecting them to the geometry of the earth itself. It's one of those inventions that doesn't just solve a problem, it expands the entire space of what's possible. Voyages that were suicidal before become merely dangerous. Trade routes that were seasonal become year-round. The world gets smaller. The compass reached Europe probably around the 12th century, likely through Arab traders, though the exact transmission route is murky. And European sailors adopted it eagerly. But here's what I find fascinating. For centuries, people used the compass without having any real understanding of why it worked. They knew the needle pointed north. They knew it was reliable enough to bet their lives on, but they didn't know what it was responding to. Was it the North Star pulling on the needle? Was it a giant magnetic mountain at the North Pole? That was actually a popular theory, that somewhere up near the pole, there was an enormous mountain of lodestone, and that's what attracted compass needles. Some map makers even drew it on their charts. And this is a pattern you see again and again in the history of technology. practical use runs way ahead of theoretical understanding. People were navigating oceans with magnetism for 300 or 400 years before anyone did a rigorous scientific study of what magnetism actually was. The engineering came first. The science came later. That's not how we usually tell the story. We like to pretend that scientists figure things out in labs and then engineers apply the knowledge. But historically, it very often goes the other way around. Someone builds a thing that works, and then, sometimes centuries later, someone else figures out why it works. The person who finally sat down and did the serious scientific work on magnetism, the first person to really treat it as a subject for careful, systematic investigation, was an English physician named William Gilbert. And Gilbert is one of those figures in the history of science who deserves to be far more famous than he is. He was born in 1544 in Colchester, England, studied at Cambridge, became a successful doctor, and eventually served as personal physician to Queen Elizabeth I. But his real passion was natural philosophy, what we'd call science, and he spent nearly 20 years conducting experiments on magnetism and electricity before publishing his masterwork in 1600. The book was called De Magnete, On the Magnet, and it's one of the most important scientific texts ever written, right up there with Newton's Principia or Darwin's Origin of Species in terms of its impact on how people understood the natural world. And what makes it so remarkable is not just the conclusions Gilbert reached, but the way he reached them. He did experiments. Careful, repeatable, methodical experiments. In an era when most natural philosophers were still arguing about what Aristotle had said, Gilbert was actually testing things. He built his own instruments. He carved lodestones into spheres. He called them terrellas, little earths, and then mapped how compass needles behaved at different positions around the sphere. And what he found was extraordinary. The compass needle didn't just point north-south when you held it near the terrella, it also dipped. Near the equator of the little sphere, the needle lay flat, but as you moved the needle toward the poles of the sphere, it tilted, angling more and more steeply downward until, right at the pole, it pointed straight down. And this matched exactly what sailors had been noticing with real compasses on real voyages, that as you sailed further north, the compass needle developed an increasing tendency to dip toward the ground. Gilbert's terrella was reproducing the behavior of the entire Earth in miniature. And from this, Gilbert drew his great conclusion. The Earth itself is a giant magnet. That's why compasses point north, not because of a magnetic mountain, not because of the stars. The whole planet is magnetic, with a north pole and a south pole, and the compass needle is simply aligning itself with the Earth's magnetic field. This was a genuinely radical idea in 1600. He was saying that the Earth, this enormous ball of rock and water and air, had an invisible force extending out from it into space, influencing any magnetized needle anywhere on its surface. It was one of the first times anyone had proposed a truly global, planetary-scale physical phenomenon and backed it up with experimental evidence. Now, Gilbert also made some mistakes. He thought magnetism was the force that held the planets in their orbits, which it isn't. That's gravity, as Newton would show about 90 years later. And he thought the Earth's magnetism was perfectly aligned with its rotation axis, which it isn't quite. There's a difference between magnetic north and true north, and that difference, called magnetic declination, actually varies from place to place and changes over time. But his core insight, the Earth is a magnet, and that's what compasses respond to, was absolutely correct. and it transformed how people thought about both magnetism and the planet they lived on. Here's something else Gilbert did that matters enormously, even though it seems like a small thing. He drew a clear distinction between magnetism and electricity. See, the Greeks had also noticed that amber, fossilized tree resin called electron in Greek, which is where we get the word electricity, could attract small objects like bits of straw after you rubbed it on fur. And for a long time, people lumped these two phenomena together. Lodestones attract iron, rubbed amber attracts straw. It's basically the same thing, right? Gilbert said no. He showed that they behaved differently in several important ways. Magnetism works only on iron and a few other materials. Electrical attraction works on many different substances. Magnetism doesn't require rubbing or preparation. A lodestone is always magnetic. Amber only attracts things after it's been rubbed. And magnetic attraction can't be blocked by putting a piece of paper between the magnet and the iron, but electrical attraction can be disrupted more easily. By carefully separating these two forces, Gilbert actually set the stage for one of the greatest surprises in all of physics. A surprise that wouldn't come for another 220 years, when someone would discover that electricity and magnetism, which Gilbert had so carefully distinguished, were actually two sides of the same coin. And the person who stumbled onto that connection wasn't even looking for it. His name was Hans Christian Ørsted. He was a Danish physicist and chemist, born in 1777, and by the spring of 1820, he was a professor at the University of Copenhagen. Now, Ørsted had actually been thinking about a possible link between electricity and magnetism for years. He had this philosophical hunch, influenced by the German Romantic tradition of nature philosophy, which held that all the forces of nature were fundamentally unified, that electricity, magnetism, heat, light, and chemical reactions were all expressions of some deeper, single force. It's a beautiful idea, and in some ways it turns out to be remarkably prescient, but at the time it was considered a bit mystical, a bit hand-wavy. Most serious physicists thought electricity and magnetism were completely separate phenomena. Gilbert had said so 2 centuries earlier, and nothing since had contradicted him. But Ørsted kept wondering. And then, in April of 1820, during a lecture demonstration, and this is one of those moments in the history of science that feels almost too perfect, he noticed something strange. He was showing his students how a wire heats up when you pass an electric current through it. He had a compass sitting on the table nearby, and when he connected the wire to the battery and current started flowing, the compass needle moved, it deflected, it swung away from north and pointed in a different direction. Now, here's what's important. The needle didn't point toward the wire or away from it, the way you'd expect if the wire were simply acting like a little magnet pulling on the needle. It swung sideways, perpendicular to the wire. That was deeply weird. Nothing in anyone's understanding of either electricity or magnetism predicted that. Gravity pulls things straight toward the center of the Earth. Electric charges attract or repel along the line connecting them. But this was a force that seemed to wrap around the wire in a circle. Ørsted didn't fully understand what he'd seen that day. He spent the next several months experimenting carefully, confirming that the effect was real, that it was consistent, that it depended on the direction of the current. If you reversed the current, the needle swung the other way. If you moved the compass above the wire instead of below it, the deflection reversed. The magnetic effect formed a kind of invisible pattern that circled the wire like rings around a finger. He published his results in July 1820 in a short Latin pamphlet that he sent to scientific societies across Europe. and the effect was immediate. This was an earthquake. Think about what he'd shown. A moving electric charge, because that's what a current is, charges flowing through a wire, creates a magnetic field around it. Not an electric field, a magnetic field. The kind of field that moves compass needles. The kind of field that lodestones have. Electricity, when it moves, becomes magnetism. Gilbert's careful distinction between the two forces was correct as far as it went. Static electricity and magnetism do behave differently. But it missed something profound. When charges move, something new happens, something magnetic. The news reached Paris within weeks, and a French physicist named André-Marie Ampère basically lost his mind with excitement. I mean that in the best possible way. Ampère was brilliant, intense, and had lived a life marked by tragedy. His father was guillotined during the French Revolution when André-Marie was just 18, and the trauma shaped him deeply. He threw himself into science with a kind of desperate focus, and when he heard about Ørsted's discovery in September 1820, he became consumed by it. Within a single week, 1 week, he had worked out the first mathematical description of the force between two current-carrying wires. And here's what he found, which is genuinely beautiful. If you run current through two parallel wires in the same direction, the wires attract each other. If you run the currents in opposite directions, they repel. 2 wires. No magnets anywhere. Just flowing electricity. And yet they push and pull on each other as if they were magnets. Ampère realized that magnetism itself, the magnetism of lodestones, of compass needles, of the earth, might be nothing more than the result of tiny electric currents circulating inside matter. He proposed that inside a permanent magnet, there are countless little loops of electric current, all aligned in the same direction, and that their combined effect is what we experience as magnetism. That's a staggering idea. Let it sit for a moment. Every magnet you've ever held, every compass needle that's ever pointed north, every magnetic latch on a cabinet door, Ampère was saying that all of it comes from electric charges in motion, not from some separate, mysterious magnetic substance, from electricity, moving electricity. Now, he didn't have the tools to explain what those tiny currents actually were. That would require understanding atoms and electrons, which wouldn't come for another 70 or 80 years. But the core idea was right. And it's one of those insights that, once you hear it, changes how you see everything. The next time you stick a magnet to your refrigerator, you're watching the collective effect of trillions upon trillions of tiny current loops inside that magnet, all spinning in roughly the same direction, all creating their own little magnetic fields that add up into something strong enough to hold a piece of paper against a steel door. But anyway, the point is that Ørsted showed that electricity can create magnetism. And almost immediately, people started asking the obvious next question. Can magnetism create electricity? If moving charges produce a magnetic field, can a magnetic field somehow produce moving charges? Can you run the process in reverse? This is where Michael Faraday enters the story, and honestly, Faraday might be the most remarkable figure in the entire history of physics. He was born in 1791 in South London, the son of a blacksmith who had moved to the city from the north of England. The family was poor. Faraday had almost no formal education. He left school at 13 and was apprenticed to a bookbinder. But he read the books that came through the shop, especially the science books, and he became fascinated by chemistry and electricity. He started attending public lectures at the Royal Institution, given by the famous chemist Humphrey Davy, and he took meticulous notes, bound them beautifully, He was a bookbinder after all, and sent them to Davy as a kind of job application. Davy was impressed enough to hire him as a laboratory assistant in 1813, and from that position, with no university degree, no mathematical training to speak of, Faraday would go on to make discoveries that rival anything Newton or Einstein ever did. He's one of those people who makes you rethink every assumption about who gets to do science and what kind of mind it takes. Faraday heard about Ørsted's and Ampere's work, and he became obsessed with the relationship between electricity and magnetism. In 1821, he built a device that was essentially the first electric motor, a wire carrying current that rotated continuously around a magnet, driven by the circular magnetic force that Ørsted had discovered. It was crude, just a wire dipping into a cup of mercury with a magnet in the middle, but it demonstrated that you could convert electrical energy into continuous mechanical motion. That's the principle behind every electric motor in the world today. Every fan, every washing machine, every electric car, it all traces back to Faraday's little mercury cup in 1821. But the bigger question still nagged at him. Could he go the other way? Could he use a magnet to generate electricity? He tried on and off for 10 years. He'd place a magnet near a wire connected to a galvanometer, a device that detects electric current, and watch for a deflection. Nothing. He'd set up the strongest magnets he could find, arrange wires near them in every configuration he could think of, and get nothing. The galvanometer just sat there, needle motionless. And here's the thing that makes this story so human. The reason he kept failing wasn't that the effect didn't exist. It was that he was looking for the wrong thing. He was looking for a steady current produced by a stationary magnet. He'd put the magnet next to the wire, watch the galvanometer, and see nothing. What he didn't realize, what nobody realized, was that you need change. You need motion or variation. A stationary magnet sitting next to a stationary wire does absolutely nothing but move the magnet or change the magnetic field in some way, and suddenly, current flows. He finally cracked it on August 29, 1831. He had wound 2 separate coils of wire around an iron ring. Think of it like a donut wrapped with wire on both sides. One coil was connected to a battery, the other to a galvanometer. When he connected the battery, sending current through the first coil and creating a magnetic field in the iron ring, the galvanometer on the second coil jumped, just for an instant. Then it settled back to 0. When he disconnected the battery, it jumped again, in the opposite direction. Then, back to 0. Only during the change, only during the moment when the magnetic field was increasing or decreasing, did the second coil produce any current. A steady magnetic field produced nothing. A changing magnetic field produced electricity. This is electromagnetic induction, and it is, without exaggeration, one of the most important discoveries in the history of human civilization. Every power plant on Earth, coal, gas, nuclear, hydroelectric, wind, generates electricity by spinning magnets near coils of wire. That's it. That's the fundamental mechanism. You change a magnetic field near a conductor, and current flows. Faraday figured this out with an iron ring and some wire in a basement laboratory in London, and it powers the modern world. Within weeks, he'd built a simpler version, a copper disc spinning between the poles of a magnet, producing a continuous current. The first true electric generator. He called it a new electrical machine. It was about the size of a dinner plate. Today, the generators at a large power station can weigh hundreds of tons and produce enough electricity for 1 million homes. But the principle is identical to what Faraday demonstrated in 1831. Now, Faraday was not a mathematician. He thought in pictures, in physical intuitions, in what he called lines of force. He would sprinkle iron filings around a magnet and study the patterns they made, those beautiful curves arcing from one pole to the other. And he believed those patterns represented something real, not just a mathematical convenience, but an actual physical thing existing in the space around the magnet. He called it a field. And this idea, this concept of a field, an invisible something that fills space and exerts forces on objects within it, was radical. Most physicists at the time thought forces acted at a distance, instantaneously, through empty space. Two magnets just somehow knew about each other across the gap between them. Faraday said no. He said the magnet creates something in the space around it, and that something is what acts on the other magnet. The force is an action at a distance. It's local. It's mediated by this field that permeates the space between them. This was an incredibly deep insight, and most of the mathematical physicists of the day didn't take it very seriously. Faraday couldn't express it in equations, and in the culture of 19th century physics, that meant it was considered vague, qualitative, not quite rigorous. But there was one young Scottish physicist who read Faraday's papers and saw something extraordinary in them. His name was James Clerk Maxwell, and what he did with Faraday's intuitions would change the course of physics forever. Maxwell was born in Edinburgh in 1831, the very same year Faraday discovered electromagnetic induction, which is one of those coincidences that feels almost too perfect. He grew up on a country estate in southwestern Scotland, a place called Glenlair, surrounded by rolling hills and farmland. And from a very young age, he was relentlessly curious. His childhood nickname was Dafty, which gives you a sense of how his constant questioning struck the other kids. He wanted to know how everything worked. "What's the go of that?" he'd ask over and over. "What's the go of it? What makes it do what it does?" And if you gave him an answer, he'd follow up with, "But what's the particular go of it?" He wanted the deeper mechanism, always. By the time Maxwell arrived at Cambridge in the early 1850s, he was already an extraordinary mathematician. He'd published his first scientific paper at 14, a method for drawing certain mathematical curves using a piece of string and some pins. 14 years old. But what made Maxwell truly special wasn't just raw mathematical ability. Plenty of people at Cambridge could handle equations. What set Maxwell apart was that he could think in pictures and in equations simultaneously. He could hold a physical intuition in one hand and a mathematical structure in the other and see how they mapped onto each other. And that's exactly the skill that was needed to take Faraday's field concept and turn it into something the rest of physics could work with. So here's what Maxwell did. He read Faraday's Experimental Researches in Electricity, all 3 volumes, thousands of paragraphs of meticulous experimental description. And where other mathematicians saw vague hand-waving about lines of force and fields, Maxwell saw the skeleton of a profound mathematical theory waiting to be fleshed out. He said later that he deliberately set out to translate Faraday's ideas into mathematical form, not to replace them, but to show that Faraday's physical intuitions were not just qualitatively right, they were quantitatively exact. Maxwell started by imagining the magnetic field as something like a fluid flowing through space. Not that he thought it literally was a fluid, but he used the mathematics of fluid flow, the way liquids move through pipes, the way pressure gradients drive currents of water, as an analogy to build equations describing how the field behaved. This was a technique he was brilliant at. Using one physical system you already understand as a mathematical scaffold for another system you're trying to figure out. He published his first paper on the subject in 1855, called on Faraday's lines of force, and it was essentially a translation job. He showed that Faraday's lines of force could be described by precise mathematical expressions, and that those expressions obeyed specific rules. But Maxwell wasn't done. Over the next decade, he kept pushing deeper. He developed a more elaborate mechanical model. Imagine tiny spinning cells filling all of space, like little molecular vortices, with smaller particles between them acting like idle wheels in a gear train. It sounds bizarre, and honestly, it was. Even Maxwell admitted the model was strange. But it was a thinking tool, a way to figure out what equations the field should obey. And here's what's wild. Using this strange mechanical analogy, Maxwell derived something no one expected. He found that a changing electric field should produce a magnetic field, just as Faraday had shown that a changing magnetic field produces an electric field. This was new. Faraday's induction went one direction. Changing magnetism creates electricity. Maxwell's equations said it should work the other way too. A changing electric field, even in empty space with no wires and no charges, should generate a magnetic field around it. He called this the displacement current, and it was a purely theoretical prediction. No one had observed it directly. But Maxwell trusted the mathematics, and he added this term to his equations. And the moment he did that, something remarkable fell out. When he combined all the equations together, the ones describing how electric fields are created by charges, how magnetic fields are created by currents, how changing magnetic fields create electric fields, and now how changing electric fields create magnetic fields. He found that the equations predicted waves, self-sustaining, self-propagating waves of intertwined electric and magnetic fields, leapfrogging through space. A changing electric field creates a changing magnetic field, which creates a changing electric field, which creates a changing magnetic field, on, rippling outward at a specific speed. And here's the kicker. Maxwell calculated that speed. He plugged in the known constants, the strength of electric forces and the strength of magnetic forces, values that had been measured in laboratories. And he got a number. About 310,000 kilometers per second, and the measured speed of light at the time, about 314,000 kilometers per second. The agreement was so close, it couldn't be coincidence. Maxwell wrote, in that understated way Victorian scientists had, we can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena. Think about what that means. Think about what he's saying. Light, the thing you see with, the thing that comes from the sun, the thing that bounces off every object around you, is an electromagnetic wave. It's a ripple in the same fields that make magnets stick to your refrigerator. The same force that makes a compass needle point north is, in a very real sense, the same force that lets you see. Electricity, magnetism, and light, three phenomena that seemed completely unrelated for all of human history, are all manifestations of a single underlying thing. Maxwell unified them in a set of 4 equations, published in their mature form in his 1865 paper, A Dynamical Theory of the Electromagnetic Field. Now those 4 equations, today we call them Maxwell's equations, are one of the great achievements of the human mind. Full stop. If you've ever seen them written out, they're surprisingly compact. 4 equations, each one a single line. And together they describe every electromagnetic phenomenon in the universe. Every radio wave, every X-ray, every beam of light, every magnetic field around every wire, every spark, every aurora, every signal from every cell tower, every pulse of energy from every star. All of it flows from those 4 lines. But here's the thing. When Maxwell published this work, the world didn't immediately stand up and applaud. The reaction was mixed. The mathematical formalism was dense. Maxwell's original presentation used quaternions, a mathematical system that most physicists found clunky and hard to follow. The physical predictions were extraordinary, but the electromagnetic waves Maxwell predicted hadn't actually been detected yet. Light was already known to be a wave, sure, but the idea that you could create electromagnetic waves by other means, by oscillating charges, say, was still just theory. Maxwell himself died in 1879, at only 48 years old, from abdominal cancer. He never saw the experimental confirmation of his greatest prediction. That confirmation came from Heinrich Hertz, a German physicist working in Karlsruhe. In 1887 and 1888, Hertz built an apparatus, essentially a spark gap connected to a loop of wire, and showed that when sparks jumped across the gap, they produced invisible waves that could be detected by another loop of wire across the room. Those waves traveled at the speed of light. They could be reflected, refracted, and polarized just like light. They were electromagnetic waves, exactly as Maxwell had predicted. Hertz had produced and detected radio waves for the first time in history. When asked about the practical applications of his discovery, Hertz reportedly said, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right," which is one of the great underestimations of all time, because within a decade, Guglielmo Marconi would be using those waves to send wireless telegraph signals across the Atlantic, and the entire age of radio communication would begin. So let's pause here and think about what this means for our understanding of magnetism, because we've come a very long way from lodestones and compass needles. What Maxwell showed is that magnetism is not a standalone phenomenon. It's one face of a deeper unity. Electric fields and magnetic fields are 2 aspects of a single electromagnetic field, and they're constantly interconverting. A magnetic field at its core is what you get when electric charges move or when electric fields change. That's it. That's the secret. Every magnet you've ever held, every compass needle that's ever swung north, every MRI machine that's ever imaged a human brain, all of it comes down to moving charges and changing fields. And this connects back to something Ampere proposed decades earlier, remember? He suggested that the magnetism of a permanent magnet comes from tiny circular currents inside the material. He was right, in essence, though the full explanation would have to wait for quantum mechanics in the 20th century. The electrons inside atoms aren't just sitting there, they're moving. They have angular momentum. They have something called spin, and all of that contributes to the magnetic properties of matter. But we're getting ahead of ourselves. We'll come back to that. For now, what matters is the picture Maxwell gave us. Space is filled with fields. Those fields carry energy. They propagate as waves, and those waves move at the speed of light because they are light. This is the framework that everything in modern electrical and magnetic engineering is built on. Every antenna, every transformer, every electric motor, every generator, every piece of wireless technology you've ever used. It all rests on the foundation Maxwell laid down in the 1860s, building on Faraday's experiments from the 1830s, building on Ørsted's accidental discovery in 1820, building on Gilbert's careful work with lodestones in 1600. And yet, even as Maxwell's theory was being triumphantly confirmed by Hertz's experiments, there were cracks forming. Small, subtle things that didn't quite fit. One of them had to do with the way light interacted with magnetic fields, and it was first noticed by a Dutch physicist named Peter Zeeman in 1896. He placed a flame in a strong magnetic field and watched what happened to the light it emitted. The spectral lines, those sharp specific colors that each element produces, split apart. They broadened and divided into multiple closely spaced lines when the magnetic field was turned on. This was called the Zeeman effect, and classical electromagnetic theory could sort of explain it, but not quite. The details didn't work out. The splitting patterns were wrong. The numbers didn't match. And this was one of those moments where a tiny discrepancy, a little crack in the edifice, turned out to be a doorway into an entirely new understanding of how matter actually works at its smallest scales. And that doorway? It opens into quantum mechanics. So let's walk through it together. Slowly. Because this is where magnetism gets truly strange and truly beautiful. Zeeman noticed that when you put a light source in a magnetic field, the spectral lines split. Now, classical theory, Lorenz's version of it, specifically, could predict a certain kind of splitting. Hendrik Lorentz, who was also Dutch and actually Zeeman's mentor, worked out that if you imagined electrons orbiting inside atoms like tiny charged planets, then a magnetic field would change their orbital frequencies slightly. Some orbits would speed up, some would slow down, and you'd get a triplet, the original spectral line flanked by two neighbors. One shifted a little higher in frequency, one a little lower, and for some spectral lines, that's exactly what happened. Zeeman observed it, Lorentz explained it, and in 1902 they shared the Nobel Prize for it. Beautiful. But here's the thing. For a lot of other spectral lines, the splitting was way more complicated. Instead of a neat triplet, you'd get 4 lines, or 6, or some other number that didn't fit the simple model at all. This was called the anomalous Zeeman effect, and that word anomalous is one of those wonderful terms in physics that basically means we don't understand this yet, but we're going to name it anyway. The anomalous Zeeman effect haunted physicists for over 2 decades. It was one of those problems that sat there, stubbornly refusing to yield to classical reasoning, because the answer required something nobody had thought of yet, and that something was electron spin. Now, let's slow down here, because spin is one of the most important and most confusing concepts in all of magnetism. It's the reason permanent magnets work. It's the reason iron is magnetic and copper isn't. It's the reason MRI machines can image your brain. And it's deeply, fundamentally weird. In 1925, 2 young Dutch physicists, Samuel Goudsmit and George Uhlenbeck, both in their mid-20s, proposed that the electron has an intrinsic angular momentum, not because it's literally spinning like a top, but because it behaves mathematically as if it has this built-in rotational property. They were graduate students at the time, working at Leiden, and their advisor Paul Ehrenfest encouraged them to publish the idea, even though it seemed a little crazy. The concept had been floating around in various forms. Wolfgang Pauli had already introduced something he called a two-valued quantum degree of freedom to explain certain spectral patterns, but he'd been deliberately vague about what it physically was. Goudsmit and Uhlenbeck gave it a name and a picture. The electron spins, and because it's charged, that spin creates a tiny magnetic field. Each electron is, in effect, a minuscule magnet. Now, the word spin is a bit of a trap, and it's worth pausing on this because it trips people up for years. When we say the electron spins, we don't mean it's rotating the way a basketball rotates on your finger. If you actually try to calculate the speed at which the electron's surface would need to move to produce the observed angular momentum, treating the electron as a tiny solid sphere, you get a speed faster than light, which is impossible. So it's not literally spinning. Spin is an intrinsic quantum mechanical property that has no classical analog. It's just something the electron has, the same way it has charge and mass. You can't ask, what is it really doing, in the same way you'd ask about a spinning top. It's a fundamentally quantum thing. But, and this is the key point, it produces a real, measurable magnetic moment. The electron acts like a tiny bar magnet, with a north pole and a south pole, and the strength and orientation of that tiny magnet are determined by its spin. And here's what's really clever about how nature set this up. The electron's spin can only take one of two values. In the language of quantum mechanics, the spin quantum number is 1/2, and when you measure the component of spin along any axis, say, the direction of an external magnetic field, you only ever get two results, spin up or spin down, plus 1/2 or minus 1/2 in units of the reduced Planck constant, nothing in between. It's binary, on or off, up or down. This is where the quantum in quantum mechanics really shows its teeth. In the classical world, a spinning top can have any angular momentum you like. Spin it faster, spin it slower, tilt it at any angle. But an electron? Two options. That's it. Think about what that means for magnetism. Every electron in every atom of your body, in the chair you're sitting in the walls of your room, is a tiny magnet pointing either up or down relative to any axis you choose. And the magnetic properties of all matter, every material you've ever touched, come down to how those tiny magnets arrange themselves. So let's talk about that arrangement, because this is where things get really interesting. In most materials, the electrons are paired up. And when I say paired, I mean that in each pair, one electron has spin up and the other has spin down. Their magnetic moments cancel each other out. It's like having two bar magnets stuck together pointing in opposite directions. From the outside, you see no net magnetic field. This is why most stuff isn't magnetic. Wood, plastic, glass, copper, water, the electrons are all paired, their spins cancel, and the material has no significant magnetic response. These are called diamagnetic materials, and they actually do respond to magnetic fields, but so weakly that you'd never notice in everyday life. If you put a piece of wood in a strong enough magnetic field, it gets very, very slightly repelled. There are videos online of people levitating frogs in enormously powerful magnets. That's diamagnetism in action. The frogs paired electrons creating a tiny opposing field. But it takes ridiculously strong fields to see the effect. Then there are materials where some electrons are unpaired. They don't have a partner with opposite spin, so their magnetic moment doesn't cancel out. Each unpaired electron contributes a little bit of net magnetism. These are paramagnetic materials, things like aluminum, platinum, oxygen gas. In the absence of an external magnetic field, the individual atomic magnets point in random directions, so the material as a whole isn't magnetized. But when you bring an external field near, some of those little magnets tend to align with it, and the material becomes weakly attracted. You'd need a pretty sensitive instrument to detect it with aluminum, but it's there. Remove the field, and thermal energy. Just the random jiggling of atoms at any temperature above absolute zero scrambles the alignment, and the magnetism disappears. But then, and this is the big one, there's a special class of materials where something truly remarkable happens. In iron, cobalt, nickel, and a handful of other elements and alloys, the unpaired electrons don't just passively respond to external fields. They actively cooperate with each other. Through a quantum mechanical effect called the exchange interaction, Neighboring atoms influence each other's electron spins, and they do so in a way that makes it energetically favorable for the spins to align in the same direction. This is ferromagnetism, and it's the reason you can stick a magnet to your refrigerator. The exchange interaction is worth lingering on, because it's genuinely one of the most remarkable things in all of physics, and it has no classical explanation whatsoever. It arises from the Pauli exclusion principle, the rule that says no two electrons in an atom can have the same set of quantum numbers, combined with the way electron wave functions overlap between neighboring atoms. Here's a rough way to think about it. When two atoms are close together, their outer electrons' wave functions overlap. The Pauli exclusion principle constrains how those electrons can arrange themselves. In some materials, the math works out so that the total energy of the system is lower when neighboring electrons have their spins aligned in the same direction. Lower energy means more stable, and nature always seeks lower energy states. So the spins line up, not because of any magnetic force between them. The magnetic interaction between two electron magnets is actually far too weak to explain ferromagnetism. It's a purely quantum mechanical effect, arising from the interplay of electron wave functions and the exclusion principle. Werner Heisenberg worked out the theory in 1928, building on earlier work by Dirac, and it was one of the early triumphs of quantum mechanics applied to solid-state physics. So in a ferromagnetic material like iron, you get regions where billions upon billions of electron spins are all aligned in the same direction, creating a powerful collective magnetic field. These regions are called magnetic domains, and they're typically microscopic, maybe a fraction of a millimeter across, but each one contains something like 10 to the 15 or 10 to the 17 atoms, all with their unpaired electron spins pointing the same way. Within a single domain, the material is fully magnetized, as strongly as it can possibly be. But here's the thing. In an ordinary, unmagnetized piece of iron, the domains themselves point in different directions. One domain might have all its spins pointing north. The neighboring domain might point east. Another might point south. The domains arrange themselves to minimize the total magnetic energy of the piece, and the result is that their fields mostly cancel out. From the outside, the piece of iron doesn't look magnetic. You could pick up a random iron nail, and it won't stick to your fridge, even though inside it, there are millions of domains, each one a powerful magnet in its own right. Now, what happens when you bring an external magnet near that nail? The domains that happen to be aligned with the external field grow. Their boundaries, called domain walls, shift, expanding the favorably oriented domains at the expense of the unfavorably oriented ones. And if the external field is strong enough, eventually all the domains rotate to align with it, and the nail becomes a magnet itself. This is why a magnet can pick up a nail. The magnet's field reorganizes the domains inside the nail, turning it into a temporary magnet that's attracted to the original one. And if you stroke that nail with a magnet, always in the same direction, you can get the domains to stay aligned even after you remove the external field. Now you've made a permanent magnet. The domains are locked in place by the crystal structure of the iron, by defects and grain boundaries in the metal that pin the domain walls and prevent them from moving back. This is the whole secret of permanent magnets, and it all comes down to quantum mechanics. The exchange interaction aligning spins within domains, and the material's microstructure keeping those domains locked in favorable orientations. This understanding, that magnetism in materials is fundamentally a quantum phenomenon, was one of the great intellectual achievements of the early 20th century. It explained things that had been mysteries for centuries. Why is iron magnetic but copper isn't? Because iron has 4 unpaired electrons in its 3D orbital shell, and the exchange interaction between neighboring iron atoms favors parallel alignment. Copper's 3D shell is full, all electrons paired, so there's nothing to align. Why do magnets lose their magnetism when you heat them? Because thermal energy eventually overwhelms the exchange interaction. There's a specific temperature for each ferromagnetic material, called the Curie temperature, named after Pierre Curie, who studied it in the 1890s, above which the thermal jiggling is too violent for the spins to maintain their alignment. For iron, it's about 770 degrees Celsius. Heat an iron magnet above that temperature, and it stops being magnetic. Cool it back down in the presence of a field, and it remagnetizes. Pierre Curie measured this systematically, and his wife Marie, yes, that Marie Curie, was working right alongside him in those years before she turned her attention to radioactivity. So by the late 1920s and into the 1930s, physicists had a remarkably complete picture of why materials are magnetic. Electron spin, the exchange interaction, domain theory. These concepts came together into a coherent framework that could explain diamagnetism, paramagnetism, and ferromagnetism. But the story doesn't stop there, because understanding is one thing, and engineering is another. Knowing why iron is magnetic is fascinating, but what people really wanted to know was how to make better magnets, stronger magnets, magnets that could hold their magnetization in harsh conditions, magnets for motors, generators, loudspeakers, scientific instruments. And that quest, the engineering of magnetic materials, is a story that runs right through the 20th century and into the present day, and it starts with a problem that had been nagging engineers since the very beginning of the electrical age. The problem was this: the magnets they had were, frankly, not very good. And by not very good, I mean they were weak, they were heavy, and they lost their magnetization too easily. Think about what was available in, say, 1900. If you needed a permanent magnet, a magnet that stayed magnetized on its own without any current flowing through a coil, your options were basically carbon steel, plain old hardened steel. And carbon steel magnets were decent, but they had a real limitation. They could be demagnetized pretty easily. A sharp knock, a vibration, exposure to a moderate opposing magnetic field, and the domains would start to shuffle around, and your magnet would gradually weaken. Engineers described this in terms of a property called coercivity, which is essentially a measure of how stubbornly a magnet resists being demagnetized. High coercivity means the magnet holds on to its magnetization tenaciously. Low coercivity means it gives up easily. Carbon steel had low coercivity. It was a soft magnetic material in the technical sense. And that's actually a useful distinction to hold on to: soft versus hard magnetic materials. Soft magnets are easy to magnetize and easy to demagnetize. They're great for things like transformer cores, where you want the magnetization to flip back and forth rapidly as the alternating current cycles. Hard magnets are difficult to magnetize, but once magnetized, they resist demagnetization. They're what you want for permanent magnets, the kind that stick to your fridge, the kind that sit inside a motor or a speaker. So the quest really was for harder and harder magnetic materials. Materials with higher coercivity, higher energy product, which is a combined measure of how strong the field is and how resistant it is to demagnetization. And this quest drove an enormous amount of materials science research through the entire 20th century. The first big step came from Japan, and the story is a lovely one. In 1917, a metallurgist named Kotaro Honda, working at Tohoku University in Sendai, discovered that if you added cobalt to steel, you could significantly increase the coercivity. His KS steel, as it was called, was a meaningful improvement. But the real breakthrough from Honda's group came a bit later, through one of his students, Tokushichi Mishima. In 1931, Mishima developed an alloy of iron, nickel, and aluminum that had dramatically higher coercivity than anything that had come before. This was the ancestor of what became known as alnico magnets. The name is literally just a mashup of aluminum, nickel, and cobalt, because cobalt was soon added to improve the properties further. Alnico magnets were a genuine revolution. They were several times more powerful than the best steel magnets, and they held their magnetization much more reliably. By the 1940s and 1950s, alnico magnets were everywhere. They were in loudspeakers, electric guitar pickups, electric motors, generators, all kinds of instruments. If you've ever picked up a vintage microphone from that era, or looked inside an old electric meter, the magnet in there is almost certainly alnico. Here's what's clever about how alnico works, and it connects back to that domain theory we talked about. Remember, domains are regions where all the atomic magnetic moments are aligned in the same direction. The boundaries between domains, called domain walls, are where the magnetization gradually rotates from one direction to another. When you demagnetize a material, what's happening at the microscopic level is that those domain walls are moving. They sweep through the material, shrinking the domains that are aligned with the field you want, and growing the ones that aren't. So if you want a magnet that resists demagnetization, you need to make it hard for domain walls to move. And alnico does this through its microstructure. When you heat-treat alnico in just the right way, and this is where the metallurgical art comes in, the alloy separates into two distinct phases at the nanoscale. Tiny, elongated particles of a strongly magnetic iron-cobalt phase are embedded in a weakly magnetic nickel-aluminum matrix. These particles are so small that each one is essentially a single magnetic domain. There are no domain walls inside them to move. To demagnetize one of these particles, you'd have to rotate its entire magnetization all at once, which requires a much stronger opposing field. That's where the high coercivity comes from. It's a beautiful example of engineering at the microstructural level. You're not just choosing the right atoms, you're arranging them in the right pattern at scales of tens of nanometers. But alnico had its own limitations. Despite its high magnetic strength, its coercivity, while much better than steel, still wasn't extraordinary by modern standards. And alnico magnets were brittle. They're essentially cast metal, hard and crystalline, and they crack if you drop them. They also required relatively large volumes to produce strong fields. Engineers kept pushing. The next big leap came in the 1950s and 1960s, and it came from a completely different class of materials, ceramics, specifically ferrets. Now, ferret magnets might not sound glamorous, and honestly, they're not. They're the dark gray, slightly rough-textured magnets that you find on refrigerator magnets, on magnetic clasps, on cheap speakers. They're made from iron oxide combined with other metal oxides. Barium ferrite and strontium ferrite are the most common, and they were developed largely through the work of researchers at the Philips Company in the Netherlands during the 1950s. Scientists like J.J. Wendt and others in their materials research labs in Eindhoven. Here's why ferrites matter, even though they're weaker than alnico in terms of raw magnetic field strength. Their coercivity is actually much higher than alnico's. A ferrite magnet is remarkably resistant to demagnetization. You can put it near other magnets, subject it to moderate opposing fields, knock it around, and it barely notices. And ferrets are cheap, incredibly cheap. They're made from iron oxide, essentially rust, and barium or strontium carbonate, which are abundant and inexpensive. You mix the powders, press them into shape, and sinter them. Bake them at high temperature until they fuse into a hard ceramic. The manufacturing process is simple and scalable. So even though a ferrite magnet produces a weaker field than an alnico magnet of the same size, the economics are so favorable that ferrites dominate in applications where you need a permanent magnet but don't need extreme performance. And that turns out to be a huge number of applications. By volume, ferrite magnets are still the most widely produced permanent magnets in the world today. Billions of them, every year. But for applications where you need serious magnetic muscle, where every gram matters, where the field strength has to be as high as physically possible, neither alnico nor ferrite was enough. And this is where the story takes its most dramatic turn, because the magnets that changed everything came from an unexpected place in the periodic table: the rare earth elements. Now let's talk about what rare earth actually means, because the name is misleading and it trips people up. Rare earth elements aren't particularly rare. Cerium, the most abundant rare earth, is about as common in the Earth's crust as copper. The name dates back to the 18th century, when these elements were first isolated from unusual minerals. Earths was an old term for metal oxides, and they seemed rare because they were hard to separate from each other. They're a group of 15 elements called the lanthanides, running from lanthanum to lutetium in the periodic table, plus scandium and yttrium, which behave similarly. And what makes several of them magnetically special is their electron configuration. Remember how we said iron's magnetism comes from unpaired electrons in its 3D orbital shell? Well, the rare earth elements have unpaired electrons in their 4f orbital shell, which is even more deeply buried inside the atom. And some of these elements, particularly neodymium, samarium, and dysprosium, have large numbers of unpaired 4f electrons, giving them enormous individual atomic magnetic moments. The catch is that in the pure rare earth metals, the exchange interaction between neighboring atoms is relatively weak because those 4f electrons are so deep inside the atom that they don't overlap much with the 4f electrons of neighboring atoms. So pure rare earth metals, while they can be ferromagnetic, have Curie temperatures that are often well below room temperature. Gadolinium is the exception. It's ferromagnetic at room temperature, but just barely, with a Curie temperature of about 20 degrees Celsius. So, here's the insight that changed everything, and it came together in the 1960s. What if you could combine the large magnetic moment of rare earth atoms with the strong exchange interaction of transition metals like iron or cobalt? You'd get the best of both worlds: huge magnetization and high Curie temperature. The rare earth atoms would bring the magnetic punch. The iron or cobalt atoms would provide the strong coupling that keeps everything aligned well above room temperature. The first person to really crack this open was Karl Sternat, an Austrian-born physicist working in the United States at Wright-Patterson Air Force Base in Dayton, Ohio. Yes, the Air Force was deeply interested in better magnets, because magnets are critical components in radar, communications, guidance systems, and all kinds of military hardware. In 1966, Sternat and his colleague Ray Hoffer discovered that an alloy of yttrium and cobalt, YCO5, had extraordinarily high magnetic anisotropy. Magnetic anisotropy is the property that makes a material prefer to be magnetized along one particular crystallographic direction. High anisotropy means the magnetization is locked in place, pointing one way, and it takes an enormous amount of energy to rotate it. This translates directly into high coercivity, and YCO5 had anisotropy values that dwarfed anything seen before. But yttrium isn't the most magnetically impressive rare earth. Samarium is better. And in 1967, Sternat's group showed that samarium cobalt, SMCO5, had even more spectacular properties. The coercivity was enormous. The energy product, that combined measure of field strength and resistance to demagnetization, was far beyond alnico or ferrite. And the Curie temperature was high, around 720 degrees Celsius, meaning these magnets would work reliably at elevated temperatures. Samarium cobalt magnets went into production in the early 1970s, and they were transformative. They made possible a new generation of compact, powerful motors and actuators. They went into military systems, into aerospace applications, into places where you needed a tiny magnet that could produce a field that previously would have required something 10 times its size. But samarium cobalt had a problem, and it was an economic one. Both samarium and cobalt are expensive. Cobalt, in particular, was subject to dramatic price spikes. In the late 1970s, political instability in Zaire, which was the world's dominant cobalt producer, sent cobalt prices through the roof. Engineers and materials scientists started asking an obvious question. Could you make a rare earth magnet using iron instead of cobalt? Iron is cheap, abundant, and has a strong magnetic moment. The trouble was that the binary compounds of rare earths and iron, things like SMFE5 or NDFE5, either didn't form stable crystal structures or had poor magnetic properties. The crystal chemistry just didn't cooperate. And this is where a discovery emerged that would reshape entire industries. In 1982, two groups independently found the answer, and the story of their parallel discovery is one of those wonderful episodes in science where the same insight strikes in two places at once. One group was led by Masato Sagawa at the Sumitomo Special Metals Company in Japan. The other was led by John Croat at General Motors Research Laboratories in Warren, Michigan. And what they both discovered was that if you added a small amount of boron, just a few percent, to a neodymium iron mixture, it formed a remarkable new compound, Nd2Fe14b, neodymium iron boron. The boron stabilized a crystal structure that had everything you could want: enormous magnetic anisotropy, huge saturation magnetization, because the structure was packed with iron atoms all contributing their magnetic moments, and a Curie temperature of about 310 degrees Celsius, not as high as samarium cobalt, but perfectly adequate for most applications. The energy product of these new neodymium magnets was staggering. They were roughly 10 times more powerful than ferrite magnets, and significantly stronger than samarium cobalt at a fraction of the cost. Sagawa's approach used a powder metallurgy technique, grinding the alloy into fine powder, aligning the particles in a magnetic field, pressing them into shape, and sintering. Croat's approach used a rapid solidification technique called melt spinning, producing a different microstructure. Both worked. Both produced magnets that were, by a comfortable margin, the strongest permanent magnets the world had ever seen. And here's where you start to feel the impact ripple outward into everyday life, because neodymium magnets didn't just improve existing technologies, they enabled entirely new ones. Think about how many things in your daily life depend on small, powerful, lightweight, permanent magnets. The hard drive in your computer, or the one that was in your computer before solid-state drives took over, used a neodymium magnet in its voice coil actuator, the tiny motor that swings the red-right head across the spinning disk with extraordinary precision. The earbuds in your ears, the ones producing rich, detailed sound from a device smaller than a fingertip. There's a neodymium magnet in each one. Electric vehicles use neodymium magnets in their drive motors because the combination of high field strength and low weight means you can build a motor that's compact and efficient enough to make an electric car practical. Wind turbines, the big ones, the ones generating megawatts of power on hilltops and offshore platforms, many of them use direct drive generators packed with hundreds of kilograms of neodymium magnets, eliminating the need for a heavy, maintenance-prone gearbox. The scale of neodymium magnet production today is almost hard to comprehend. Something like 150,000 to 200,000 tons per year, and the vast majority of it, we're talking over 90%, is produced in China, which also dominates the mining and processing of rare earth ores. And that concentration of supply has created its own set of geopolitical tensions, particularly since the late 2000s, when China briefly restricted rare earth exports and prices spiked dramatically. But that's a whole other thread, and what I want to stay with right now is the physics, because there's something beautiful happening inside a neodymium magnet that connects all the way back to those ideas about electron spin and exchange interactions that we were exploring earlier. In the Nd2Fe14b crystal structure, you've got layers of iron atoms providing the bulk of the magnetization through their 3D electrons, and neodymium atoms whose 4F electrons create the enormous magnetic anisotropy that locks the magnetization direction in place. The boron atoms are doing something structurally essential. They're sitting in the crystal lattice in just the right positions to stabilize the whole arrangement. It's a three-part collaboration at the atomic level. And the reason this particular combination works so spectacularly well, while countless other rare earth iron compounds don't, comes down to the specific geometry of how these atoms pack together, the distances between them, the angles, the way the electron orbitals overlap. It's the kind of thing where changing one atom, shifting one ratio, can make the difference between a world-changing material and a useless lump of metal. Sagawa spent years systematically testing different compositions before he hit on the right one, and even then, optimizing the processing, the milling, the pressing, the sintering temperatures took enormous effort and ingenuity. Now, neodymium magnets aren't perfect. They have a couple of notable weaknesses that engineers have been wrestling with ever since they were invented. The first is temperature. That Curie temperature of 310 degrees Celsius sounds high, but the practical operating limit is much lower because the coercivity starts to drop well before you reach the Curie point. At around 150 or 200 degrees Celsius, depending on the grade, a neodymium magnet can start to lose its magnetization irreversibly. For applications like electric vehicle motors, where things get hot, this is a real concern. The solution that's been developed is to add dysprosium or terbium, other rare earth elements, to the alloy, which boosts the high-temperature coercivity. But dysprosium is genuinely scarce and expensive, so there's been a huge research effort to find ways to use less of it, or to find alternative approaches entirely. One clever technique that's emerged in recent years is called grain boundary diffusion, where instead of mixing dysprosium throughout the entire magnet, you diffuse it only along the boundaries between the crystalline grains, right where it's needed most. You get most of the benefit with a fraction of the dysprosium. The second weakness is corrosion. Neodymium magnets are prone to oxidation. The neodymium-rich phase at the grain boundaries is particularly reactive. An uncoated neodymium magnet will gradually corrode, especially in humid environments, and eventually crumble. That's why almost every neodymium magnet you encounter is coated. Nickel plating is the most common, giving them that shiny silver appearance. But epoxy coatings and other treatments are also used. And then there's a third issue that's less about the magnet itself and more about what happens when you try to use it in certain applications. Neodymium magnets are incredibly strong for their size, which means the forces between them can be surprisingly dangerous. Two large neodymium magnets snapping together can easily crush a finger, and there are documented cases of serious injuries. In industrial settings, handling large neodymium magnets requires careful procedures and specialized equipment. It's one of those situations where a material's greatest strength is also, quite literally, its greatest hazard. But despite these challenges, the impact of neodymium magnets on modern technology is almost impossible to overstate. They've made possible the miniaturization of countless devices. They've made electric motors lighter and more efficient. They've enabled MRI machines to become more compact, though MRI magnets are actually superconducting electromagnets rather than permanent magnets, so that's a slightly different story. And actually, it's a story worth telling, because it takes us into one of the most extraordinary manifestations of magnetism in the physical world: superconductivity, and the way that quantum mechanics, at very low temperatures, can produce magnetic fields of almost unbelievable intensity, fields that can levitate trains and peer inside the human body without a single incision. So let's talk about that. Let's talk about what happens when you cool certain materials down to temperatures so low that the very concept of electrical resistance just vanishes. Because superconductivity is one of those phenomena that, even after you've studied it, even after you understand the mathematics, still feels like it shouldn't be real. It feels like cheating, and its relationship with magnetism is so deep, so fundamental, that you really can't tell the full story of one without the other. The discovery goes back to 1911, to a laboratory in Leiden in the Netherlands. A physicist named Heike Kamerlingh-Onnes had spent years developing techniques to liquefy gases at lower and lower temperatures. He was the first person to successfully liquefy helium in 1908, which gave him access to temperatures just a few degrees above absolute zero. That's around minus 269 degrees Celsius, or about 4 Kelvin. And once he had liquid helium, he started doing what any good physicist would do. He started measuring things. Specifically, he started measuring the electrical resistance of metals at these extreme temperatures. Now, at the time, there were competing theories about what should happen to a metal's resistance as you approached absolute zero. Some people thought resistance would gradually decrease and approach zero smoothly. Others thought it might hit a minimum and then increase again as the electrons sort of froze in place. The reality turned out to be stranger than either prediction. Kamerlingh-Onnes was measuring the resistance of mercury. He chose mercury because he could get very pure samples by distilling it. And as he cooled it down, the resistance dropped gradually, as expected. And then, at about 4.2 Kelvin, it didn't just decrease. It fell off a cliff. It dropped to zero, not approximately zero, not immeasurably small. Zero. Exactly zero, as far as any instrument could detect. He checked his equipment. He repeated the measurement. Same result. Below that critical temperature, mercury conducted electricity with absolutely no resistance whatsoever. You could start a current flowing in a loop of superconducting mercury, remove the battery, and the current would just keep flowing. Forever. Not for a long time. Forever. There's no slow decay, no gradual loss of energy to heat. The current simply persists. Experiments have monitored persistent currents in superconducting loops for years without detecting any measurable decrease. The estimated decay time, based on the precision of these measurements, is longer than the age of the universe. Think about what that means. In every normal conductor, copper wire, aluminum, gold, electrons flowing through the material are constantly bumping into impurities, into lattice vibrations, into each other, losing energy as heat. That's what resistance is. That's why wires get warm when you run current through them. That's why power companies lose a significant fraction of the electricity they generate just transmitting it through power lines. And superconductivity says none of that. Below a certain temperature, all of that friction, all of that scattering, just stops. Kamerlingh Onnes recognized immediately that this was something profound, and he won the Nobel Prize in 1913, just 2 years after the discovery. But here's the thing, the explanation for why it happened took another 46 years to arrive. For nearly half a century, superconductivity was one of the great unsolved puzzles of physics. Some of the best minds in the world took a crack at it. Einstein tried. Feynman tried. None of them could explain it within the existing framework of physics. The breakthrough came in 1957 from 3 American physicists, John Bardeen, Leon Cooper, and Robert Schrieffer. Their theory, known as BCS theory after their initials, is one of the most beautiful pieces of physics of the 20th century. And the core idea, while mathematically demanding, has an elegance that you can grasp intuitively if you think about it the right way. Here's the picture. In a normal metal, electrons repel each other. They're all negatively charged, so they push apart. But in a superconductor, at very low temperatures, something subtle happens. An electron moving through the crystal lattice slightly distorts the lattice. It pulls the positively charged atomic nuclei toward it, just a tiny bit as it passes. That slight concentration of positive charge, in turn, attracts another electron. So you end up with 2 electrons that are, in effect, coupled together through their interaction with the lattice, not directly attracted to each other, but linked through this intermediary. These paired electrons are called Cooper pairs, after Leon Cooper. Now here's where it gets really interesting. Individual electrons are fermions. They obey the Pauli exclusion principle, which means no 2 of them can occupy the same quantum state. That's the same principle we talked about earlier when we were discussing why electrons in atoms arrange themselves in shells and why the exchange interaction makes ferromagnetism possible. But a Cooper pair, 2 electrons bound together, behaves as a composite boson. And bosons play by completely different rules. Bosons can all pile into the same quantum state. They actually prefer to. So at low enough temperatures, all the Cooper pairs in the material condense into a single collective quantum state, a macroscopic quantum phenomenon, where billions upon billions of electron pairs are all doing the same thing, moving in lockstep, described by one shared wave function. And because they're all in the same state, they can't scatter individually. You can't knock one Cooper pair out of the flow without disrupting the entire collective, which requires a minimum amount of energy. An energy gap. If the thermal energy in the system is below that gap, which it is at sufficiently low temperatures, then no scattering can occur. No scattering means no resistance. The current flows without loss. It's quantum mechanics operating not at the scale of individual atoms, but at the scale of an entire wire, a centimeter-long piece of superconductor, a meter-long coil, the quantum world, made visible and tangible and useful. And now let's bring magnetism back into the picture, because superconductors have an extraordinary relationship with magnetic fields. In 1933, two German physicists, Walter Meissner and Robert Ochsenfeld, discovered something that went beyond just zero resistance. They found that when you cool a superconductor below its critical temperature in the presence of a magnetic field, the superconductor doesn't just fail to let new magnetic field in. It actively expels the magnetic field that's already there. The field gets pushed out. The interior of the superconductor becomes a zone of zero magnetic field. This is the Meissner effect, and it's what makes superconductors levitate above magnets, or, equivalently, what makes magnets levitate above superconductors. You've probably seen those dramatic demonstrations where a small magnet hovers in midair above a dish of superconducting material cooled with liquid nitrogen. That's the Meissner effect in action. The superconductor is saying, in essence, no magnetic field is allowed in here, and it generates surface currents that create an opposing field to enforce that rule. The magnet has nowhere to go, but up. This is actually what distinguishes a superconductor from a merely perfect conductor. If you had a hypothetical material with truly zero resistance but no Meissner effect, and you applied a magnetic field and then cooled it down, the field would just stay trapped inside. A true superconductor expels it. That distinction matters enormously because it tells you that superconductivity isn't just about the absence of resistance. It's a fundamentally different thermodynamic state of matter with its own distinct properties. Now, for engineering, the really important thing about superconductors is what happens when you wind them into coils and use them as electromagnets. Remember, an electromagnet works by running current through a coil of wire. The current creates a magnetic field, and the more current you push through, the stronger the field. In a normal electromagnet, you're limited by resistance. Push too much current through copper wire, and it overheats. You need cooling systems, you need enormous amounts of power, and even then there are practical limits to how strong a field you can generate. But in a superconducting electromagnet, there's no resistance. You can run enormous currents through the coil without generating any heat at all. The only energy cost is keeping the coil cold enough to remain superconducting. And the magnetic fields you can produce this way are extraordinary. 10, 15, even 20 Tesla or more, compared to the 1 or 2 Tesla you might get from a conventional iron core electromagnet. These are fields strong enough to do things that would be simply impossible any other way. And that brings us to MRI, magnetic resonance imaging, which is, for most people, the most personally significant application of superconducting magnets. If you've ever had an MRI scan, you've lain inside a superconducting magnet. The main magnet in a clinical MRI machine is typically a superconducting coil made of niobium titanium alloy, cooled to about 4 Kelvin with liquid helium, producing a field of 1.5 or 3 Tesla. That's roughly 30,000 to 60,000 times the strength of Earth's magnetic field, and that field has to be incredibly uniform, consistent to within a few parts per million across the imaging volume, because the whole technique depends on detecting tiny, subtle differences in how hydrogen atoms respond to the field. Here's how it works, at least in broad strokes. Your body is mostly water, and water is mostly hydrogen, and each hydrogen atom has a single proton at its nucleus. That proton has a property we've already encountered: spin. It behaves like a tiny magnetic dipole. Normally, these proton spins are oriented randomly, pointing in all directions, and their magnetic effects cancel out. But when you slide into that powerful MRI magnet, the protons align, some parallel to the field, some anti-parallel, and there's a slight statistical excess pointing in the direction of the field. A very slight excess, maybe a few protons per million. But when you have trillions upon trillions of hydrogen atoms, that tiny imbalance adds up to a measurable net magnetization. Then the machine hits you with a precisely tuned pulse of radio waves, radio frequency energy at exactly the resonant frequency of hydrogen protons in that particular magnetic field strength. This is the resonance in magnetic resonance. The protons absorb that energy and flip their spins. When the radio pulse stops, the protons gradually relax back to their equilibrium alignment, and as they do, they emit faint radio signals of their own. The machine listens for those signals, and here's the crucial part. The rate at which protons relax depends on their chemical environment. Protons in fat relax differently than protons in muscle. Protons in healthy tissue relax differently than protons in a tumor. By applying carefully designed sequences of magnetic field gradients, additional coils that make the field slightly stronger at one end than the other, the machine can determine exactly where in the body each signal is coming from and build up a detailed three-dimensional map of the soft tissues inside you. No radiation, no surgery, no contrast agents needed for many scans, just magnetism, radio waves, and an extraordinary amount of clever signal processing. And all of it made possible because a superconducting coil, cooled to 4 degrees above absolute zero, can sustain the intense, stable, uniform magnetic field that the whole technique demands. The current in that coil, once established, just keeps flowing. Some MRI magnets have been running continuously for years without being re-energized. There's something almost meditative about that, if you think about it. Right now, in hospitals all over the world, in the middle of the night, there are superconducting magnets humming quietly, their coils carrying currents that have been flowing without interruption for months or years, held at temperatures colder than outer space by jackets of liquid helium, generating fields powerful enough to align the nuclear spins of every hydrogen atom in a human body. And those magnets are saving lives. They're finding tumors before they become untreatable. They're mapping the intricate folds of the brain. They're showing surgeons exactly where a lesion is before they make their first cut. But MRI is just one application. Superconducting magnets show up in particle accelerators. The Large Hadron Collider at CERN uses over 1,600 superconducting dipole magnets, each about 15 meters long, cooled to 1.9 Kelvin, colder than the cosmic microwave background radiation that fills the universe. Those magnets bend the paths of protons moving at 99.9999991% of the speed of light, guiding them around a 27-kilometer ring beneath the Swiss-French border. Without superconducting magnets, you simply could not build a machine like that. The fields required would demand so much electrical power that no conventional electromagnet could sustain them. And then there's the application that sounds the most like science fiction, but is already running in daily service in several countries: magnetic levitation trains, or maglev. The basic idea is beautifully simple. Use magnetic forces to lift the train off the track, eliminating friction between wheels and rails, and then use magnetic fields to propel it forward. Japan's SC maglev system uses superconducting magnets on the train itself, cooled with onboard helium systems, interacting with coils embedded in the guideway walls. The train levitates about 10 centimeters above the track and has reached speeds over 600 kilometers per hour in testing. Shanghai's commercial maglev, which uses a different technology based on conventional electromagnets rather than superconductors, runs at over 430 kilometers per hour in regular passenger service. But the superconducting approach promises even higher speeds and greater efficiency for longer routes. What connects all of these applications, MRI, particle physics, maglev, is the same fundamental insight. Superconducting materials, held at cryogenic temperatures, allow you to create magnetic fields of a strength and stability that would be completely impractical with conventional conductors. They let you do things with magnetism that would otherwise require impossible amounts of power, impossible amounts of cooling, impossible amounts of copper. They take the basic principle that Ørsted stumbled onto in 1820, electric current creates a magnetic field, and push it to extremes that he could never have imagined. But there's a catch, and it's a significant one. All of the superconductors I've been describing, niobium titanium, niobium tin, the materials used in MRI machines and particle accelerators, are what we call low-temperature superconductors. They only work at temperatures close to absolute zero, which means you need liquid helium to cool them, and liquid helium is expensive, scarce, and tricky to handle. For decades, physicists assumed that superconductivity was fundamentally a low-temperature phenomenon, that it could never occur at temperatures much above about 30 Kelvin. The BCS theory seemed to impose limits on how warm a superconductor could be. And then, in 1986, something happened that turned the entire field upside down. At an IBM research laboratory in Zurich, two physicists named Georg Bednorz and Alex Mueller were doing something that most of their colleagues considered a waste of time. They were looking for superconductivity in ceramic materials, in oxides, in compounds, that most physicists would have bet everything could never superconduct. Ceramics are brittle. They're insulators, for the most part. They're the stuff you make coffee mugs and floor tiles out of. The idea that you could find superconductivity in a ceramic oxide was, to put it politely, eccentric. And Bednorz and Mueller knew it. They worked quietly, almost secretively, because they didn't want to attract the kind of skepticism that might get their project shut down before they had results. But here's the thing about Bednorz and Mueller. They had a hunch, and it was rooted in something real. Mueller, the senior of the two, had spent years thinking about a class of materials called perovskites, which have a very specific crystal structure. Imagine a cube with one type of atom at each corner, a different atom in the center, and oxygen atoms sitting at the center of each face. It's a beautifully symmetric arrangement, and Mueller had a feeling, not quite a theory, more like an informed intuition, that the particular way electrons interact with the lattice vibrations in these structures might support superconductivity at higher temperatures than anyone expected. Bednorz, who was younger and had expertise in crystal growth, started systematically working through different compositions, different combinations of elements in that perovskite framework, looking for any sign of a superconducting transition. And in January of 1986, they found it. A compound of barium, lanthanum, copper, and oxygen, what's now called LbCO, showed signs of superconductivity at around 35 Kelvin. Now, 35 Kelvin is still absurdly cold by everyday standards. It's about minus 238 degrees Celsius. But in the world of superconductivity, it was revolutionary, because it shattered the theoretical ceiling that BCS theory seemed to impose. 30 Kelvin had been treated as more or less the upper limit for decades, and here was a ceramic, blowing past it. They published their results in September of 1986, in a paper with one of the most understated titles in physics history. Something like, Possible High TC Superconductivity in the BALACUO System. Possible. They were being careful. And at first, the reaction was muted. A lot of physicists simply didn't believe it. Ceramics? Superconducting? Above 30 Kelvin? It sounded like an error, but then other labs started replicating the results. And then, in early 1987, things went absolutely wild. A physicist at the University of Houston, named Paul Chu, along with his collaborator Ma Quen-Wu at the University of Alabama, started tweaking the composition. They replaced lanthanum with yttrium, and what they found made international headlines. Their new compound, yttrium barium copper oxide, which everyone now calls YbCO, became superconducting at 93 Kelvin. 93 Kelvin. And that number matters enormously, because liquid nitrogen boils at 77 Kelvin. Do you see what that means? For the first time in history, you had a superconductor that could be cooled with liquid nitrogen instead of liquid helium. And liquid nitrogen is cheap. It's roughly the cost of milk. You can buy it by the liter without breaking anyone's budget. Liquid helium, by contrast, is hundreds of times more expensive and requires specialized equipment to handle. Crossing that liquid nitrogen threshold was like going from needing a private jet to catching a city bus. It changed the economics of superconductivity overnight. What followed was one of the most frenzied periods in the history of physics. The March 1987 meeting of the American Physical Society, held at the New York Hilton, became legendary. The session on high-temperature superconductivity ran from the evening straight through until about 3 in the morning, with thousands of physicists crammed into a ballroom, spilling into the hallways, watching on closed-circuit television in overflow rooms. People were presenting results that were days or even hours old. It was dubbed the Woodstock of physics, and for good reason. There was a genuine feeling that the world was about to change, that room temperature superconductivity might be just around the corner, that we were on the verge of lossless power transmission, levitating trains everywhere, a complete revolution in technology. Bednorz and Muller won the Nobel Prize in Physics in 1987, just a year after their discovery. That almost never happens. The Nobel Committee usually waits decades to make sure a discovery holds up. The speed of the award tells you how significant the physics community considered this breakthrough. Now, I should be honest with you about what happened next, because the story of high-temperature superconductors is not a simple triumph. It's more complicated, and in some ways more interesting, than the breathless headlines of 1987 suggested. The room temperature superconductor that everyone was dreaming about? We still don't have it, not in any practical, confirmed, reproducible way. The critical temperatures kept climbing for a while. Other copper oxide compounds pushed past 130 Kelvin, and under extreme pressure, some materials have shown signs of superconductivity above 200 Kelvin. But the dream of a material that superconducts at room temperature and atmospheric pressure, something you could just hold in your hand and use without any cooling at all, that remains elusive. And the high-temperature superconductors we do have come with serious practical challenges. Remember, these are ceramics. They're brittle. You can't draw them into wires the way you can with niobium titanium. Try to bend a piece of YbCO, and it snaps. Making useful conductors out of these materials has required decades of materials engineering, developing techniques to deposit thin films of the superconductor onto flexible metal tapes, creating what are called coated conductors or second-generation high-temperature superconducting wire. It works, but it's expensive and finicky. The grain boundaries in these polycrystalline ceramics can block the flow of supercurrent unless the crystal grains are very carefully aligned, so you need extraordinary control over the manufacturing process. But here's what's really interesting. Despite all those challenges, high-temperature superconductors are starting to find their way into real applications, and some of them are directly relevant to things we talked about earlier. Think about those massive wind turbine generators we discussed, the ones that use neodymium magnets. There's a competing approach that uses superconducting coils instead of permanent magnets. A high-temperature superconducting generator can be significantly smaller and lighter than a permanent magnet generator of the same power rating, which matters enormously when you're trying to put a generator on top of a tower 100 meters in the air, out at sea. Several companies and research groups have been developing superconducting wind turbine generators, and while they're not yet widespread, the technology is maturing. Or think about fusion energy. The quest to build a working fusion reactor, essentially recreating the process that powers the sun here on Earth, depends critically on magnetic confinement. You need incredibly strong magnetic fields to contain a plasma heated to hundreds of millions of degrees, keeping it suspended away from the walls of the reactor because no physical material can withstand that temperature. The most promising reactor design, called a tokamak, uses enormous magnets arranged in a donut shape to confine the plasma. And the strength of those magnets directly determines how compact and efficient the reactor can be. For decades, tokamak designs relied on low-temperature superconductors. The ITER project in Nauamois, France, which is the world's largest fusion experiment currently under construction, uses niobium tin magnets cooled with liquid helium. But a company called Commonwealth Fusion Systems, spun out of MIT, made a dramatic bet on high-temperature superconductors. They built a magnet using REBCO tape, that's rare earth barium copper oxide, a cousin of YBCO, and in 2021, they demonstrated a 20 Tesla magnet, the strongest of its kind ever built with high-temperature superconducting technology. 20 Tesla. That's roughly the strength of the most powerful MRI research magnets, but in a configuration designed for fusion confinement. The stronger your magnets, the smaller your tokamak can be, and the smaller it is, the cheaper and faster you can build it. This is one of those cases where a breakthrough in magnetism could unlock an entirely different field of engineering, and that connection between understanding magnetism at a fundamental level and solving enormous practical problems is really the thread that runs through this whole story, isn't it? From Ørsted's accidental discovery with a compass needle, through Faraday's intuitive field lines, through Maxwell's equations unifying light and magnetism, through the quantum revolution that explained why iron is magnetic in the first place, through the engineering of permanent magnets and superconducting coils. It's all one continuous thread. Each generation builds on what came before, and each breakthrough opens doors that the previous generation couldn't even see. And there's one more piece of this story that I want to spend some time with, because it might be the most pervasive application of magnetism in your daily life, and yet it's one that most people never think about. It's not in your refrigerator magnets or your headphones or even your car's electric motor, though all of those matter. It's in the thing you're probably lying next to right now, your phone, your laptop, whatever device is playing this for you. And it has to do with how we store and process information using magnetism, a story that starts with a Danish engineer named Valdemar Poulsen and a steel wire, way back in 1898. Poulsen was working at the Copenhagen Telephone Company, and he had this idea that seems almost obvious in hindsight, but was genuinely radical at the time. He wanted to record sound, not onto a wax cylinder, not onto a disc with grooves, but onto magnetism itself. His device, which he called the telegraphone, worked like this. You had a thin steel wire, stretched taut and moving past an electromagnet. When someone spoke into a microphone, the sound waves were converted into an electrical signal. We've talked about how that works. It's just Faraday's induction running in reverse, essentially. And that fluctuating electrical signal was fed into the electromagnet, As the wire moved past, the varying magnetic field magnetized each tiny segment of the wire to a different degree. The pattern of magnetization along the wire was a physical record of the sound. To play it back, you just ran the wire past the electromagnet again, and the magnetized segments induced tiny currents that could be amplified and sent to a speaker. Sound, captured as a magnetic pattern. Poulsen actually demonstrated this at the 1900 World's Fair in Paris, and the recording he made there, a snippet of Emperor Franz Joseph's voice, is believed to be the oldest surviving magnetic recording. It's scratchy and faint, but it exists. And here's what's remarkable about Poulsen's insight. He understood that magnetism could be a medium for information. Not just a force, not just a curiosity, not just a way to generate electricity or stick things to your fridge, but a way to write and read data. Now, the telegraphone didn't take off commercially. The signals were too weak. Amplification technology wasn't there yet. Vacuum tube amplifiers wouldn't become practical for another couple of decades. And honestly, wax cylinders and phonograph discs worked well enough for most people. Poulsen spent years trying to commercialize his invention and largely struggled. But the idea didn't die. It just waited for the technology to catch up. And catch up it did. In the 1930s, German engineers at AEG and the chemical company IG Farben developed something that changed everything. Magnetic tape. Instead of a steel wire, they coated a thin plastic ribbon with fine particles of iron oxide. Gamma iron oxide, to be specific, Fe2O3. Tiny needle-shaped particles, each one a miniature permanent magnet. When you ran this tape past a recording head, which was just a small electromagnet with a gap in it, the fringing magnetic field at that gap magnetized the particles on the tape. Each particle got locked into a particular orientation, and the pattern of orientations along the tape encoded the signal. The German device was called the magnetophone, and by the late 1930s, it was producing recordings of astonishing quality. When Allied forces captured Radio Luxembourg in 1944, they found magnetophone machines and were stunned by the audio fidelity. The recordings sounded live. American engineer Jack Mullen brought 2 of those machines home after the war, demonstrated them in Hollywood, and Bing Crosby, of all people, became a crucial early backer. Crosby wanted to pre-record his radio shows instead of performing them live twice for the East and West Coasts, and magnetic tape made that possible. His investment helped launch the Ampex Corporation, which became the dominant name in professional tape recording. But I want you to think about what's happening at the particle level, because it connects back to everything we've talked about. Each one of those iron oxide particles on the tape is a tiny magnetic domain, essentially. When the recording head magnetizes it, it's aligning the magnetic moments of the atoms within that particle. The coercivity of the material, how strongly it resists being demagnetized, determines how well the recording lasts. Too low, and the recording fades. Too high, and you can't write to it in the first place. The whole art of magnetic recording media is finding materials with just the right coercivity, just the right particle size, just the right shape anisotropy. It's domain engineering, the same principles we talked about with permanent magnets, but applied to information storage. And this is where the story takes its most consequential turn. Because tape was wonderful for audio, and later for video, the VCR, if you're old enough to remember those. But the real revolution came when engineers realized you could store not just analog waveforms on magnetic media, but digital data. Ones and zeros. Magnetized one way, that's a 1. Magnetized the other way, That's a zero. And if you could make the magnetized regions small enough and pack them close enough together, you could store enormous amounts of information in a very small space. The hard disk drive. This is the device that made the modern computing era possible, and it's pure applied magnetism from top to bottom. IBM built the first one in 1956, the Ramac 305, it was called. It was the size of 2 refrigerators. It contained 50 aluminum disks, each 2 feet in diameter, coated with iron oxide paint. And it stored, are you ready for this? 5 megabytes. 5 megabytes in a machine that weighed over a ton. You could fit maybe one MP3 song on it. IBM leased it to companies for about $3,000 a month, which in today's money is something like $30,000 per month for 5 megabytes. But the principle was brilliant, and it scaled. A hard disk drive works like this. You have a rigid disk, originally aluminum, later glass or ceramic, coated with a thin magnetic film. The disk spins at high speed, thousands of revolutions per minute. A tiny read-write head floats just above the surface on a cushion of air. And when I say just above, I mean the gap between the head and the disk surface in a modern drive is something like 10 nanometers. That's about 50 atoms. If you scaled the disk up to the size of a football field, the head would be flying at the equivalent of a few millimeters off the ground at supersonic speed. It's an absurd engineering feat when you think about it. To write data, the head generates a localized magnetic field that flips the magnetization of a tiny region on the disk. To read data, the head detects the magnetic orientation of each region as it flies past. And the story of hard drives over the past 7 decades is really the story of making those magnetic regions smaller and smaller and smaller, packing more bits into every square inch of disk surface. In 1956, the areal density, the number of bits per square inch, was about 2,000. By the year 2000, it was around 10 billion. Today, it's in the trillions. That's a factor of roughly a billion improvement in storage density over 60-some years. There might not be another engineering metric in history that has improved by a factor of a billion. And one of the key breakthroughs that made this possible is so elegant, it won a Nobel Prize. It's called giant magnetoresistance, GMR, and it was discovered independently by Albert Fert in France and Peter Grunberg in Germany in 1988. Here's the idea. If you make a sandwich of 2 thin ferromagnetic layers separated by a very thin non-magnetic spacer, we're talking layers just a few nanometers thick, the electrical resistance of that sandwich depends dramatically on whether the 2 magnetic layers are magnetized in the same direction or opposite directions. When they're aligned the same way, electrons with matching spin pass through easily, and the resistance is low. When they're anti-aligned, both spin types get scattered, and the resistance is high. The change in resistance can be enormous, tens of %, which is why it's called giant magnetoresistance. Now, think about what that gives you. You have a sensor whose electrical resistance changes depending on the magnetic field it's exposed to. Mount that sensor on your red head, fly it over the disk, and as it passes over regions magnetized in different directions, its resistance flickers up and down. Those resistance changes are your data, your ones and zeros. And because GMR heads are so sensitive, they can detect much smaller magnetic regions than the older inductive heads could. Smaller regions mean higher density. Higher density means more storage in the same space. Fert and Grunberg won the 2007 Nobel Prize in Physics for this, and the Nobel Committee explicitly noted that it was a beautiful example of how fundamental physics research, they were just studying thin magnetic films out of curiosity, led to transformative technology. By the time they won the prize, GMR red heads were already in virtually every hard drive on the planet, and the successor technology, tunnel magnetoresistance or TMR, was taking over, offering even greater sensitivity. So when you think about the device next to you right now, the one playing this narration, whether it has a hard drive or a solid-state drive, whether it's streaming from a server farm somewhere, magnetism is woven into the infrastructure at every level. Those server farms that store the world's data, many of them still rely heavily on hard disk drives for bulk storage, spinning platters coated in cobalt platinum alloys, read by TMR heads, storing trillions of bits per square inch. The data flows to you through networks that run on electricity generated, in many cases, by spinning magnets and turbines. Faraday's principle, still at work. The signal might pass through transformers that step voltage up and down. Faraday again. If it reaches you wirelessly, it's carried by electromagnetic waves. Maxwell's equations, confirmed by Hertz, commercialized by Marconi. And here's what I find quietly astonishing about all of this. Every single piece of that chain traces back to someone staring at a compass needle, or winding wire around an iron ring, or scribbling equations by candlelight, or arguing about whether atoms could really spin. The people who figured out magnetism, Gilbert with his lodestones, Ørsted with his lecture demonstration, Ampere with his mathematical intensity, Faraday with his unshakable physical intuition, Maxwell with his beautiful, terrifying equations, Curie with her meticulous temperature measurements, Goudsmit and Uhlenbeck with their electron spin, Heisenberg with his exchange interaction. None of them could have imagined a world where their discoveries would let someone lie in bed and listen to a stranger talk about magnetism while drifting off to sleep. But here we are. And the story isn't over, of course. It never is with science. Right now, researchers are working on spintronics, devices that use the spin of electrons rather than just their charge to process information. There are people designing magnetic random access memory, MRAM, which could replace conventional RAM and give your computer instant-on capability because magnetic states don't vanish when you cut the power. There are teams working on skyrmions, tiny, topologically stable magnetic structures that could serve as the basis for a completely new kind of data storage, denser and more energy efficient than anything we have today. There are the fusion researchers we talked about, betting that superconducting magnets will give us clean energy. There are quantum computing groups using superconducting circuits to build qubits. The magnetic story keeps branching and growing, and each branch connects back to that same trunk, the slow, painstaking, sometimes accidental, often beautiful accumulation of understanding about how magnetic fields work, where they come from, and what we can do with them. So if you're still awake, and it's perfectly fine if you're not, honestly, that's sort of the point. I hope some of this has settled into a comfortable place in your mind. Magnetism is one of those subjects that seems simple on the surface. Magnets stick to fridges, compasses point north, sure. But the deeper you go, the more extraordinary it becomes. It connects the spin of individual electrons to the structure of the cosmos. It links ancient sailors navigating by lodestone to particle physicists smashing protons together at nearly the speed of light. It's in the earth beneath you, and the stars above you, and the device beside you, and, in a very real quantum mechanical sense, in every atom of your body. And maybe that's a nice thought to drift off with, that you're lying there, made of atoms, each one containing electrons with their own tiny magnetic moments, all doing their quantum mechanical thing, mostly canceling each other out so you don't stick to the refrigerator, which is probably for the best. But there, quietly, fundamentally, magnetic. Part of the same story that started with a strange rock in Magnesia, thousands of years ago, that could pull iron toward it for reasons nobody understood. We understand it now. Not completely, not perfectly. There are still open questions. There always are. But deeply, beautifully, usefully. And that understanding took centuries of curiosity, argument, experiment, failure, and insight from people all over the world, building on each other's work. One generation handing the next a slightly better map of how the universe works. That's the story of magnetism. And now, if you haven't already, you can let it go. Let your thoughts soften and sleep.